The last thing I want to talk about is the work that builds upon this interactive proof ideas and this arithmetization ideas and using polynomials, using algebra, that has to do with Np-Hardness of Approximations. So far we talked about decision problems, and we talked about 3-SAT as NP-complete problems. So it's very difficult to tell satisfiable formulas from unsatisfiable formulas. But in real life, we often talk about approximation algorithms, which don't find the optimal solution to some optimization problem, but only approximately optimal to some factor approximations. And it would be nice to say something about the difficulty of solving those natural optimization problems approximately even. And that's exactly what we can do using the ideas of probabilistically checkable proofs that I'm going to talk about next. So let me start with our good old friend, free satisfiability. We're given 3CNF phi on M clauses. Natural question to ask is, how many clauses of phi can we satisfy simultaneously? Okay, one obvious answer is, well, if phi is satisfiable, then all M clauses can be satisfied simultaneously. And if phi is not satisfiable, then fewer than M clauses can be satisfied simultaneously. That's correct, but not very satisfying. Forgive me my pun. So if the formula is not satisfiable, then the number of clauses that can be simultaneously satisfied obviously must be strictly less than M, the total number of clauses. How much smaller than M can it be? Well, we're going to show that for any formula phi, satisfiable or unsatisfiable, it's always possible to satisfy at least 7/8 fraction of the clauses. Okay, and this is a very simple argument that I will show you. That's a fact. You can always satisfy at least 7/8 of M clauses in a given collection of M clauses. And the proof is by probabilistic method. You look at the particular clause on 3 literals, like this one in the example. And if you think about random assignment that you pick uniformly, the probability that this clause is satisfied will be exactly 1 minus 1/8. 1/8 is the probability that the clause is not satisfied. You really need to be unlucky and pick xi to be 0, xj to be 1, and xk to be 0. Only one choice out of 8 possibilities for these 3 literals will make the clause false. So with probability 1 minus 1/8, which is 7/8, this clause will be true. So the expected number of satisfied clauses, if you pick a random assignment, by simple argument, is 7/8 times M, because each clause is satisfied with probability 7/8. M clauses, the expected number of satisfied ones is 7/8 times M. And by probabilistic argument, if the expectation is 7/8 over M, then there must be at least one assignment which satisfies at least 7/8 times M clauses. Okay, so we tightened a little bit the possibilities for unsatisfiable formulas in terms of how many simultaneously satisfied clauses they can have. So we know that unsatisfiable formulas live somewhere around here. They have the number of simultaneously satisfied clauses somewhere between 7/8 M and strictly less than M. But they can be anywhere in this range as far as we know. Can we somehow push the number of satisfied clauses closer to the left edge of this interval, make them closer to 7/8 times M? And the answer is yes. And that's possible thanks to this optimal result due to Johann Hofstede from around 1997, which can be viewed as an equivalent statement of the PCP theorem. PCP theorem, of course, is it's a work of many people. I'm not giving the history of the results here. I'm just stating one particular way of stating the PCP theorem with 3 CNFs due to Hofstede. So the statement is the following. fix some constant epsilon bigger than 0, okay, like 1 over 10. Then there exists a polynomial time reduction from 3 sat to 3 sat. Sounds a bit suspicious. Why do you need to reduce 3 sat to 3 sat? Well, because the conditions will be different from the usual reduction that we had seen before in the context of NP completeness. So the reduction R will be the following. It will take a 3CNF phi and will map it to another 3CNF R of phi, satisfying the following two conditions. If the original formula phi was satisfiable, then the new formula R of phi will also be satisfiable. More interestingly, if the original formula phi was not satisfiable, then the new formula R of phi will be at most 7/8 plus epsilon satisfiable, meaning that at most 7/8 plus epsilon fraction of the clauses of the formula R of phi can be simultaneously satisfied. Okay, so we basically take a formula phi and transform it into a new 3CNF formula such that if the formula was satisfiable, the number of satisfied clauses will stay on the right-hand side here. But if the formula was unsatisfiable before, the new formula will have the number of satisfying assignments living somewhere on the left side of the interval, 7/8 plus epsilon times m. Okay, and there will be nothing in between here. So we have a gap between the number of clauses that can be simultaneously satisfied. As a corollary of this result, we can say that it's NP hard to distinguish satisfiable 3-sat formulas from 7/8 plus epsilon satisfiable ones, where 7/8 plus epsilon satisfiable are exactly those where you can satisfy 7/8 plus epsilon fraction of clauses. And in turn, this can be interpreted as saying that an optimization problem max 3-sat, which asks, given a formula, find the maximum number of clauses that can be simultaneously satisfied. So this optimization problem, maximize the number of clauses simultaneously satisfied, that this optimization problem is NP hard to approximate, C approximate, where C, the approximation factor, is 8/7 plus epsilon, which is tight because of this probabilistic argument that I mentioned earlier. For completeness, I state what it means for a problem, optimization problem like max sat to be C approximated. Basically means that you need to find a value V, which is at most the optimal value, which is the maximum number of satisfying assignments, opt of phi, but at least 1 over C fraction of the optimal value. Okay, so 1 over C in case C is 8/7 plus epsilon is going to be roughly 7/8 plus epsilon. Finally, another way we can use this reduction from 3-sat to 3-sat in Hosted's result is to think about the following generalization or refinement of the gain between the prover and the verifier that we defined when we defined NP problems to begin with. So think of the following refinement. You have prover and verifier. You have 3CNF formula phi, which is a common input to the prover and the verifier. The prover will send some bit string of polynomial limiting bits, t, to the verifier. And in the usual definition of NP, the verifier will just take this assignment, plug it into the formula phi, and check if formula phi is satisfiable. That would involve looking at the entire assignment, y1 through yt. We don't want to do that. Our verifier will be very lazy. It will randomly select some collection of at most 3 bits in the string y and check that those bits satisfy some constraint, and with very good probability will catch incorrect proof, incorrect witness that the prover will send to the verifier. So more precisely, here's what's going to happen. The verifier on input phi will construct the new 3CNF psi, which is R of phi, where R is the reduction from Hofstade's theorem. This constructed psi will have some T number of variables, polynomial many, and some M polynomial many number of clauses. Then the verifier will pick a random clause out of this M1s, call it Ci, and will accept if and only if this clause, C sub I, is satisfied by the corresponding 3 bits from the bit string Y. Okay, so the verifier will randomly select a clause using small amount of randomness, about log n bits of randomness, because there are only polynomial many clauses. And then we'll only look at the proof sent by the prover in 3 locations corresponding to the variables mentioned in that clause C sub I, and accept if those 3 bits in the proof Y satisfy that chosen randomly closed C sub I. And the properties we get from this is that if phi was satisfiable, then there exists a proof Y sent by the prover that the verifier will consult using its randomly chosen locations to check, and the verifier will accept with probability 1, because if phi was satisfiable, the new formula R of phi will also be satisfiable. So if the prover is honest and will send the correct satisfying assignment, every clause chosen by the verifier will be satisfied. On the other hand, if the formula phi is not satisfiable, then no matter what assignment prover sends to the verifier, the fraction of clauses that can be simultaneously satisfied in this formula R of phi is going to be at most 7/8 plus epsilon. So if the verifier picks a clause at random, the probability that he gets a satisfied clause is at most 7/8 plus epsilon. So with probability 1 minus that, with probability about 1/8, the verifier will see a clause which is not satisfied and will reject. Okay, so a verifier can be lazy, can only read small number of 3 bits from the proof. It will have to be randomized to pick which position to pick by using randomness. And then it can check if the proof was good or not. This is quite amazing that you don't need to read the entire satisfying assignment of the formula, but if you massage the formulas appropriately, then you can it's sufficient for you to read only constant number of 3 bits of the new proof for the new formula and have pretty good confidence in accepting correct witnesses, correct proofs, and with decent constant probability rejecting incorrect proofs with very little work done. And that concludes this part of the online tutorial, and we'll continue with more stuff to talk about in the online part during the bootcamp.